Welcome, everyone. I'm Ira Feldman. I'm the MEPTEC Executive Director. I'd like to say good morning, good afternoon, good evening, wherever you're joining us from. Thank you for joining us today at the MEPTEC IMAPS Semiconductor Industry Speakers Series. Upcoming talks in the series are November 11th, Tim Orsley of Corning will talk about ribbon illumina. And then on November 25th, David Keelet from Intel will talk about chiplet technology. December 9th, Sandeep Razdan from Cisco will provide the presentation. And then as a special holiday treat, we're going to do something as a different format on December 16th that we're calling our Holiday Hangout. It should be a lot of fun, so please plan to join us for that. Just a reminder, MEPTEC is a membership and sponsorship-driven organization, so please either join us as a member, renew your membership, or please join us as a corporate sponsor. If you have questions about joining or sponsoring, please reach out to Betty, bcooper@meptec.org. So today, I'm happy to present Chuan Xie of Xilinx. He's going to talk about co-packaged optical I/O, the promise and the challenges. Chuan has been involved in several technology companies in Silicon Valley, including Harmonic, Infineon, and Intel, Amkor, and Sumitomo. In 2014, while he was at Sumitomo, he became involved in silicon photonics, and he joined as principal engineer at Xilinx in the Silicon Technology Group in early 2017. He holds a BS degree in quantum electronics from Peking University and a PhD in physics from SUNY Stony Brook. So I'm very happy to welcome Chuan.
Thank you, Ira, for the introduction. And thanks everybody for coming to the presentation today. So this is the title of my talk for the day. It's co-packaged optical I/O, the promise and the challenges. So this is the outline of the talk. So I'll begin with a definition of what the co-packaged optical I/O is. Then I'm going to discuss why we are doing the co-packaged optical I/O. And followed by that is a status of the technology development where we are today. And I'm going to emphasize some of the challenges we are still trying to address today. So what is co-packaged optical I/O? Obviously, it's the optical I/O is going to be inside the IC package, but the optical transceiver itself is not part of the core IC, but a separate entity sitting on a silicon interposer or some other packaging substrate. So the optical transceiver is also referred to as electro-optical converter or optical engines, especially by many photonics companies. So this optical transceiver will have an interface to the core IC. This interface is electrical, low power, highly parallel, and the data rate may be lower for low power consumption. And the external interface is optical, directly interfacing to the optical fibers. The optical I/O optical interface will have high speed optical channels with high bandwidth density. in recent years, you probably see many cartoons of how this co-packaged optical interface would look like. They more or less all look like this. This particular one is from Intel. Okay, why do we want to package the optical I/O together with the large-scale communication integrated circuit? So to answer that question, so we need to understand how we've been doing optical communications today. So at the bottom here, I kind of copied a little diagram from OIF. So this is CEI 112G VSR. So basically, you have the chip, which is the IC, like a switch IC. So then it actually moves the data to and from the optical transceiver modules, which are mounted on the faceplate. So through PCB, and so the VSR needs to cover 8 inches of PCB traces. So it usually has 12 to 16 dB of loss at Nyquist frequency of 28 gigahertz. So because of this low bandwidth and high loss to high frequency signals, you need to use FEC and a lot of equalization in order to achieve error-free communication between the IC and the electrical interface of the optical transceiver. So that will consume a lot of power, and also the FEC will consume some, will have some bandwidth overhead, add additional power consumption, and more importantly, adding latency. So, another limitation today is the aggregated bandwidth. So in the middle of the slide here, I put a little picture of the QSFP-DD. This is kind of like the cutting edge optical transceiver today. And this transceiver can provide 400 gigabit per second bandwidth. And such a transceiver will only give 22 gigabit per second per millimeter edge bandwidth density. You can actually mount 36 such transceiver ports on a 1 RU line card. So this will support a 14.4 terabit per second total bandwidth. So if the bandwidth of a switch IC goes to 50 terabit per second, or even 100 terabit per second, the traditional standalone optical transceiver will fall way short in providing the total bandwidth needed. So realizing this, bandwidth challenge, DARPA actually, as part of the Electronics Resurgence Initiative, started a program called the PIPES program. And we are actually one of the participants, we being Xilinx. So according to this PIPES program, the target for the energy efficiency in phase 1 is 2.5 picojoule per second per bit, and the aggregate bandwidth density, the aggregate bandwidth is 10 terabit per second, and the bandwidth density is 1 terabit per millimeter. So that's way more than an order of magnitude higher than today's optical transceiver can provide. In phase 2 and 3, that bandwidth density increases to 2 terabit per second. That's almost like 100 times that we can achieve today with standalone optical transceivers. And also the energy efficiency target is 2.5 picojoule per bit in phase 1, and that becomes 1 picojoule per bit in phase 2 and 3. So the energy efficiency for these QSFP-DD module can be easily estimated. So the 400G QSFP-DD module has a power consumption of 12 watts. So that gives you the energy efficiency of 30 picojoule per bit. That is just for the optical module itself. For a good comparison, you also need to include the electrical I/O of the chip itself. So that can the total energy efficiency is easily in the neighborhood of 40 picojoule per bit. So if we get even close to the pipe's target of phase 1, 2.5 picojoule per bit, that's more than 10 times improvement in energy efficiency. I think that the...
So are you still in phase 1, or how long is phase 1 expected to run?
Yeah, we're still in phase 1. Actually, we're getting close to the later part, to the end of that. Phase 1 actually officially ends in February of 2021. But you know, due to the COVID situation, we are experiencing some delay. So more likely, we're going to extend that by a couple of months.
Yeah. And are things looking good to hit the target? Or, I mean, that's a pretty substantial change.
We haven't really had the test data in yet, but based on our current estimate, we're going to get fairly close to the 2.5 picojoule per bit. But this is based on an optimistic estimate on the laser power consumption itself. I'm going to cover the light source a little bit more detail later. So,
and just for people, I'm sorry, there was a question. I mean, how long is this program? How long has phase 1 been running?
Okay, so pipes is I think it's a 3.5 years program. So phase 1 is 18 months. So it officially started in August of last year, 2019. So then after phase 1, there is a 12-month phase 2, and followed by another 12-month phase 3.
Thank you.
So basically, to summarize the motivation for co-packaged optics, the problem we're trying to address really is threefold. One is to improve energy efficiency dramatically. So even if we don't hit this 2.5 picojoule or 1 picojoule per bit target, if we hit like 4 or 5 picojoule per bit, that's still close to tenfold of improvement compared to the state of the art today. And the bandwidth density improvement will have to rely on a technology called WDM. Basically, optically, you can put multiple optical channels on a single fiber. That's going to dramatically increase the bandwidth, edge bandwidth density. And another motivation is to get rid of FEC, forward error correction. So if we achieve this goal, the latency will be improved significantly. Okay, so the basic technology that we need to rely on to achieve this goal is silicon photonics. So I'm trying to cover silicon photonics very briefly on a high level. Silicon photonics, of course, is a wide field, but the focus here, of course, is on the datacom side of it. So what is silicon photonics? Silicon photonics basically is to build photonics components and circuits on silicon wafers using CMOS compatible processes. So if we can do that, we can leverage the volume production capability in CMOS fabs, and also have access to all the advanced process and metrology tools. So silicon photonics needs to be built on SOI wafers, because the buried oxide layer is actually needed as the bottom cladding for the silicon waveguides. Silicon is transparent to the common wavelengths used in communication, namely 1.31, the 1310 nanometer wavelength, which is also referred to as the O band, or the 1550 nanometer wavelength, which is referred to as the C band. So silicon actually makes excellent waveguide because of the high index contrast between silicon and silicon dioxide, which is actually the cladding for the waveguide. The silicon waveguide is called a strong guiding waveguide. So it can be made very small in width. Typical single mode silicon waveguide is less than 0.5 micron in width. And because of the strong guiding, you can make pretty sharp bending of the waveguide without much bending loss. The typical band radius for silicon waveguide can be below 5 microns. So in the past decade or two, a lot of high quality passive components are made available on silicon, but with the exception of some otherwise successful WDM components. I'll cover that a little bit later. So for high-speed modulation, actually silicon has some challenge in being an effective modulator because of the crystal symmetry. It lacks the linear or quadratic electro-optical effect. So, but fortunately, silicon is a semiconductor. So we can use the so-called plasma dispersion effect. Basically, the index of refraction of silicon changes with the carrier density. So that's the phenomenon that's that most of today's silicon modulators are based on. And we can readily grow using epitaxial growth of germanium on silicon. So this is a mature process, and germanium on silicon provides the means for optical detection. So, so we can make very high speed photodetectors, both in the O band and C band. Germanium with some addition of silicon in it also provides a way to make electro-absorption modulators based on the Franz-Kaldish effect. So basically, when you apply a voltage, the band gap of germanium will shrink, and you can use that to make an electro-absorption modulator. But silicon photonics does face some fundamental challenges. But most of these challenges, fortunately, there are ways to sort of get around them. On top of the list is the fact that silicon does not generate light with electrical pumping. Since silicon is an indirect bandgap semiconductor, so when carriers recombine, you don't get photons, you get phonons, which is essentially heat. So the solution to this is, well, there's two solutions people commonly use today. One is to die bond 3,5 GaN medium on the silicon wafer directly to make lasers. There's some efforts trying to make a more native light source on silicon, but those are still in research stage and not practical yet. So another solution is to use off-wafer external light source. And I think this approach is getting favored by a lot of companies at this point, because it actually segregates two difficult technologies, sort of mitigate the risk. So another issue with silicon waveguide is the phase error, which is not easily controlled through process. So what this actually means is that if you have a very small variation in the waveguide width, or if your SOI thickness is slightly different across the wafer or from wafer to wafer, that's going to cause a large phase error in silicon based passive devices. So this poses a big challenge to make some WDM devices, such as AWG or Ixhao grading. There's a lot of research going into this, but because of this phase error, that's not easily controlled, these devices unfortunately not manufacturable at this point. So the way to get around it, of course, is to do phase tuning. So this phase tuning actually works on some relatively simpler devices, such as Mach center interferometer or ring resonators. So there's two ways to tune the phase. One is thermal tuning. So when you change the temperature of silicon, its index changes. So you can use that to tune the phase of a silicon, for example, a silicon interferometer or a silicon ring resonator. Another way to tune it, of course, is to use the carrier density tuning through carrier injection into silicon. So the third challenge is temperature sensitivity. This actually works both ways. On the negative side, when you make, for example, a silicon resonator, it hits one frequency, resonance frequency at, say, room temperature. When the temperature changes, that resonance frequency or wavelengths will change with temperature. So, of course, the way to counter that is, again, to use thermal tuning. Of course, there's also ways to design devices that's athermal. So you basically introduce some other material with a negative temperature coefficient to counter the index change of silicon with temperature. So here I show this is some real data that we collected in the PIPES program. On the top right here, I show the same device, same range resonator on one wafer in 20 different reticle locations. You can see the resonance wavelengths is kind of all over the place. So the distance between two adjacent resonance of the same device is called the free spectral range. You can see that the free spectral range of all these different devices is very consistent across the wafer, but the actual resonance wavelength is filling a big portion of free spectral range, meaning that they're more or less just random. Okay, but if you have devices close by on a small, in a small area on the same wafer, the phase error will be better. So at the bottom here is 8 different microrange modulators. We design them to have actually equal spectral resonance wavelength separation. You can see that you don't really achieve uniform spacing, but all these channels are at least in the right sequence. So, in a real situation, we actually apply thermal tuning to all these devices, then we can actually even equalize the channel spacing.
So there were some questions on WDM. I don't know whether you want to talk about them here or later in your deck.
Maybe we can talk about that a little later.
Okay, great.
Yeah. Okay. So technology choices. So basically, there's different ways to build a silicon modulator. So the commonly used modulators MZM, which is based on the Mach-Zehnder interferometer. So there is also the micro-ring modulator and the electro absorption modulator, which I actually mentioned earlier. So both actually work with good speed, but they have different characteristics. So MZM modulators are really robust, and the technology is also pretty mature. But it's actually a very good choice for modulators in a standalone optical transceiver. But for co-packaged optics, it has the disadvantage of higher power consumption and large size. So here I have a little picture showing 2 types of MZMs on the same die. So on the left-hand side, you see 3 kind of folded MZM. These are segmented MZMs. So basically, because of the large size of the modulator, you can't treat it as a lumped component anymore. So one way to design a high-speed modulator is to actually separate the long arms of the modulator into different sections, and you drive each section separately, and you control the relative delay so that you can achieve a high modulation at high speed. Okay, another way is to use a traveling wave design. So basically you have a transmission line. So your electrical signal and optical signal will just travel down the modulator simultaneously if their speed is roughly matched. So you get a traveling wave modulator. But either approach will require a pretty long device on the order of 2 to 3 millimeters in length. So that obviously takes up a lot of space on the die. Contrary to that, the micro-ring modulator is much more compact. The ring modulator is typically, for high-speed modulation, is less, the radius is less than 10 microns for sure, closer to 5 microns. Typically, so the size of the modulator is 10 to 20 microns across. So that provides a much more compact solution, and also the power consumption needed to drive such a device is much smaller compared to the Mach center modulators. The EA modulator is also compact, relatively small. Usually the length is less than 100 microns. But the issue there is that it only works for the C band, but for data centers, O band is usually the preferred wavelength. And also it's difficult to make EAM work with WDM. So therefore, based on that, the best modulator choice for co-packaged optics is the micro-ring modulator. On the detection side, it's germanium photodetector, but there is also a PIN or pin detector or APD detector. APD is avalanche photodetector, so that can provide GaN and hence give you some better sensitivity. But it also requires a higher voltage, and also it's challenged to work at a very high bandwidth. So a more mature device is still germanium pin detector by far. Okay.
On the modulators, there was a question. Is there a huge power difference between the MZM and the MRM? Is there any relative figures of merit, or
Yeah, so yeah, there is a very significant difference between them. The one way to think about it is that if you think about a segmented MZM, right? So say you have a let's say you have a 2 millimeter long modulator, and you probably for 50 gigabit per second operation, you probably need to divide it into like 10 segments in order to treat each segment as a lumped device. So if you do that, you have to drive these 10 pieces independently, each with the driver by itself. So, and the drivers also need to have controlled delay. So each of these drivers will probably equivalent to the power consumption of a single MRM driver. So I don't have the exact number, but if you use this analogy, the power consumption can easily be up to 10-fold.
Thank you.
But for a standalone transceiver, you have a bigger power budget, and that's probably not a big deal because your benchmark is against other 3.5 based approaches. But for a integrated I/O, you do want higher energy efficiency. So since I say that the microwave modulator may be the best choice for co-packaged optical I/O, so I go a little bit more detail on that. So first of all, on the right-hand side here, I'm just trying to show that the speed of the modulator is quite good. So this is actually data from our lab at Xilinx from a collaboration we have with IMAPS. So on top here, you see a 56 gigabit per second NRZ optical I. And at the bottom here, you see a 100 gigabit optical I PAM4. And at the lower right here is basically S21 measurement from a microwave modulator. The bandwidth is well over 35 gigahertz. So, and the upper left here is a little diagram showing how we do WDM with these modulators. So, assuming that you have a multi-line light source with evenly spaced optical channels unmodulated coming in. So then since the array modulator are resonance devices, so if you tune different modulators to different laser lines, then you will modulate all these optical channels individually without having to demultiplex the laser channels. And on the receive side, you can also use ring based optical filters to drop each individual optical signals to individual photodetectors and do the detection there. So it works well if you have a WDM light source.
So with that, I mean, one of the questions is how many wavelengths do you think are practical with WDM? I mean, are we talking 8, 16, more? I mean, you're talking 5
so
here.
Yeah, that's a good question. So actually, a short answer to that is full pipes. We're trying 16 lambda. The limitation there is this, right? So actually, if I go back to this slide, you can see that I say the microwave modulator actually works well with DWDM. It doesn't work with CWDM. That is because the range of wavelengths is limited by the free spectral range of the modulator, which is depends on the actual modulator size. It's typically between close to 10 nanometers to maybe even over 20 nanometers, depends on the size of the modulator that you design. So that basically limits the range of wavelengths for WDM. And another limitation here is crosstalk. So you have, on this plot, you have these individual modulators modulating individual laser lines coming in, right? So, but the modulator itself has a Q factor, which is not infinitely big. Actually, for high speed, that Q factor has to be relatively low, maybe around 4,000, 5,000. So that means each modulator will have a tail. So each modulator actually can also modulate a laser line that comes close to its resonance wavelength. So therefore, in order to avoid crosstalk, you need to set a minimum separation between channels. So given these two, basically, you have a bounded number of channels you can support. Yeah, but with the way we actually do in our plan is 8 channel. We say 16 channels because we actually do one stage of interleaving. So when the channel comes in, it has 16 colors. We actually use device called the interleaver. We separate the even channels from the odd channels. That way, we actually open up, we widen the channel spacing by a factor of 2 to avoid crosstalk.
Got it. And just one other question on the modulator. I mean, what kind of optical insertion loss, I mean, or power loss do you get through this MRM?
Okay. Right. So, so we can today we have proven that a 6 dB of modulation loss. Let me explain that, what that means. Actually, you have a DC unmodulated light coming into your modulator. So then you have modulated signal going out. So the optical modulation amplitude, or OMA, basically the power difference between your 1 level and 0 level, that is called the optical modulation amplitude. So the OMA is 6 dB below your incoming DC power. Say you have 1 milliwatt of optical power coming into a ring modulator, you can get a 1/4 milliwatt of modulation amplitude coming out. So, and we are trying to push for a better result. I think we have a target in phase 2. I hope we can hit it, but there's no guarantee at this point. We can hit that like 4 dB of modulation loss.
That would be a nice improvement. Okay, thank you.
Yeah, we need that to cover the link budget that's required for the later phases. Okay. So so this slide covers some architectural options. So basically, how you go about making these transceivers. The number one architectural choice is whether you do monolithic or heterogeneous integration between the optical functions and the electrical functions. For the optical transceiver, you need the modulator driver. You also need the TIA for the detector, right? So these are electrical functions. So by monolithic, I mean, you integrate these electrical functions on the same die or on the same wafer as your optical components. So in the early days of silicon photonics, I think this is actually one of the value propositions. You can put everything on the same wafer. And that indeed was what people did at that time. Actually, Lextera, which is now part of Cisco, their first 40G silicon photonics-based optical transceiver was done monolithically. Basically, everything is on the same die. But more recently, maybe in the past 5 years or so, people started to favor more of this heterogeneous approach. So basically, you make your electrical functionality on the EIC, and you make your optical functionality on the PIC. Then you combine these two dies in packaging. So this offers a lot more flexibility because photonics and electronics favor different SOI. So the photonics obviously needs a much thicker box for the to avoid the light from penetrating through the bottom cladding and gets lost in the substrate. But electronics usually don't like a thick box, and also the process node. Photonics, you don't need a very high advanced process node. Typically, people do it with 90 nanometers, even 130 nanometer technology node, or some do it at 65, but nobody is doing it at 7 or 28 or 16. But electronics, of course, for low power consumption and high speed, you would favor the most advanced process node. So, but monolithic approach is still alive. For the obvious advantages, which is cost, you only tape out one die, one wafer. And also you eliminate the assembly process between the E-die and the PIC. A good example is that Global Foundries had this 9GG, which supports, which is a 90 nanometer process that supports both CMOS devices and optical components. And they are now migrating to this 45 CLO, which is a 45 nanometer process. But I don't think they are going to go beyond 45 for good reasons. Yeah. Another one is the coupling options. There's edge coupling and also surface coupling. Surface coupling is through surface grating couplers. And the limitation there is grating couplers actually has some wavelength dependency, but the window usually is wide enough for the WDM applications. Yeah, we already talked about this. The range of wavelengths is limited by the remodulator's free spectral range, so that falls actually within the window of the transmission window of the gratings. And grating couplers are polarization dependent. So if you know the polarization, you can use a one-dimensional, simpler one-dimensional grating coupler. But if you, on the receiver side, your incoming polarization can be both TE or TM or a combination of the two. So you have to use the 2D grating coupler, and 2D grating coupler usually has higher loss. But one big advantage of surface coupling is it facilitates on-wafer testing, because you can have optical access through the grating couplers. Also, there's some interesting development right now. Grating couplers coupled with microlens can give you some kind of at least on paper, it looks very promising option to use optical connectors to eliminate active alignment. And also, this may be a better alternative than fiber pigtails for a large package. Edge coupling, of course, has a V-grooved edge coupling, which is designed to have the fibers butt couple to the edge of the spot size converter in a passive alignment procedure. Unfortunately, V groups and TSV are kind of not compatible, because if you have TSV through your PIC optical wafer, then the wafer needs to be thinned, and thinning the wafer obviously is not a good thing for these edged V groups. Right? So these two processes are not compatible. And another approach, of course, is to just have a spot size converter to the edge of the die and do the coupling using free space optics. And this is not favorable because it requires active alignment.
So with just a quick question, with these coupling options, I mean, so it has to be performed before, let's say, the package is encapsulated. You can't, you've got to get all this right before you seal the package.
Right, that's a very good question. I think it's the jury is still out, and whether you you put down the optical transceivers on the package substrate before you do the fiber alignment, or you attach the fiber to the optical transceivers, then you assemble those transceivers on the package. I think both methods have pros and cons, of course. Just as you mentioned, if you do the coupling at the last step, what if the part is defective? Then you have to throw away the whole thing, right? So and also, but if you do the optical fiber attachment first, then your optical fiber pigtail and everything needs to be able to sustain the reflow process, the subsequent reflow process. Yeah, of course, the fiber needs to be attached before the final. If you have a lid for the whole package, then that goes on the last. Okay, so the status, I started by talking about the ecosystem. So yeah, there's obviously a market demand for this. So the data center and HPC customers really want this to become a reality. An example of that is Microsoft and Facebook recently formed a co-packaged optics collaboration. You can actually find more details from this website. And of course, because of that, the IC companies, Xilinx included, really evaluating the feasibility. You know that Intel has been working on silicon photonics for a long time. And initially, there was this grand promise from silicon photonics. Then they switched to making silicon photonics-based standalone optical transceivers. Now, at least in recent years, you see a lot of activities of their R&D group doing some co-package related R&D work with excellent publications. And many startup companies are also working on what they normally call the optical engines for co-packaging. And some established photonics companies are also investing in R&D effort. So a good example of this is that recently, actually in May, there is a MSA formed trying to define the WDM channel plan for co-packaged optics. And here I copied from their website. It's called CW WDM MSA. And from the membership list, you can see there's a lot of interest in this area. Okay, so EDA tool vendors are looking at this for quite some time. Both Cadence and Synopsys are investing and making good progress in the past year or two. The challenges for doing photonics compared to electronics, one that seems kind of trivial, but it's actually a big deal, is that for electronics layout, everything is either a rectangle or a polygon. But in photonics, in order to make waveguides, you need to have support. The tool needs to support curvilinear. Basically, you need to make a circle. You need to make a smooth band and things of that nature in layout. That's actually a big step forward for these tool vendors. And also, device models support of co-simulation, and also photonics LVS. That's also a kind of a challenging thing because there's some unique features in photonics circuits that you need to be able to support. Foundries. So R&D fabs have been supporting MPW, like small scale R&D efforts for a long time, but recently we also see some smaller commercial foundries offering that. So that kind of service, you can either make prototypes through MPW, or you can even order dedicated wafer runs. And we know that global foundries, with the heritage from IBM, has been doing photonics, silicon photonics processing. And originally, I think the process node is called 9WG. It's a 90 nanometer based technology that supports both CMOS and photonics. And right now, they are finalizing this new process node called 45 SPCLO. I think SP stands for silicon photonics, CLO at C-band, L-band, and O-band. Right, so other major foundries are also testing the waters. For example, TSMC, and back then it was still Luxtera, but now it's part of Cisco. But 2-3 years ago, they actually announced a collaboration. So now Luxtera or Cisco is fabbing their photonics transceiver wafers at TSMC, and TSMC, as we know, also investigating, putting some resources into developing their own PDK for photonics. But so far, there's no public announcement, or they're not taking commercial customers at this point. Also, in order to complete the package, you also need a lot of fiber pigtails and connectors and stuff. Single mode fiber ribbons and multi-fiber connectors is actually gained some traction in traditional, conventional optical transceivers that actually can lead to the initial needs for the co-packaged optics as well. But of course, in order to reach the type of bandwidth density, there's probably more work that needs to be done in this area. So now I'm going to talk about the challenges the whole industry is still trying to address. On top of the list again is a robust and efficient WDM light source. So the light source actually can be made, WDM light source can be made using traditional DFB laser arrays and muxing techniques, but that's not really, well, yeah, that's not a very elegant way of addressing this. And it's not necessarily the most energy efficient way to do it. But there's some promising comb laser sources that's being worked on. So I'll cover that a little bit on a separate slide. The wafer level testing is a big thing. At this point, I think nobody has investigated seriously in this area much yet. But knowing identifying the known good die is very critical, because otherwise the cost will be very significant if you put unyielded die in a huge package. So wafer level testing actually for optics is kind of one of the bottlenecks, because it actually would involve optical alignment, which could potentially be time consuming. So I think I cut out a little picture, and it's not very clear here, from one of the GF's brochures. Actually, you can see there's 2 fiber probes here. And then there is an electrical probe with multiple electrical contacts. This the green triangle here. So basically, you need to. This is based on, of course, grating coupler based photonics. You can use these fiber probes to send light in and take light out, and you can use the electrical probe to apply bias voltages, for example. And this is only for DC testing. Of course, you know, each time you move to a new die, you probably need to retweak the alignment. And so it's going to be more time consuming. It requires more automation to do it right. And what about for the design using edge coupling? And that's actually still a big question mark. Potentially, we can put some small test circuit next to the main die and provide grating couplers for those and use the test data from the PCM process control parts. But would that give sufficient information for the actual die itself is still debatable. Okay, so optical assembly, this is actually a big deal. First of all, you know, fiber coupling and alignment is a new process in IC packaging, and the process needs to be developed. Right now, at this point, I think IBM has been invested quite a bit in doing the optical fiber assembly. I think in Europe, there's Tyndall also doing this kind of development work. How do you combine that with other packaging processes is still a challenge. And if the design requires active alignment, that's going to be even trickier because active alignment is even challenging in traditional transceiver manufacturing. It's normally higher cost and low throughput. Okay, so and from a design standpoint, there's a lot of work that needs to be done to cut down the insertion loss and coupling loss. Because low loss means higher energy efficiency, but more importantly, we need the optical signal to actually reach the potential of error-free operation, so we can minimize the requirement of forward error correction for low latency. Okay, so continue with the challenges. Fiber management actually is going to be a big deal. The fiber management in traditional optical transceiver is already kind of an industry on its own. But if you look at this little cartoon of co-packaged optics, so they have like 16 fiber ribbons attached to the edge on all 4 sides. So even if you assume that each one of these ribbon is 12 fibers, that gives you close to 200 fibers. So we're going to have hundreds of fibers coming out from the package in multiple fiber ribbons. How are we going to manage these fibers? And actually, I put a question mark here. Really, are we going to do fiber ribbons from all sides? maybe not in the beginning, because bending the fiber over, if this is the front to the faceplate, this direction is easy, and the back direction may be okay. You can easily loop the ribbon fiber over, but on the side, you have to kind of twist it somewhat. So it's going to be a nightmare trying to manage all these fibers. And also, what about fiber breakout, right? So not necessarily all single ribbon will go to the same destination. So we probably need some breakout or patch panel to arrange the fibers. Okay, so with a package with so many different fibers, what if there is a single fiber breakage? That's going to be very painful. So therefore, in my view, if we can use some little free space based connectors that can plug into the edge of the package, leave the fiber cable totally out of the package itself, that'll be a more ideal solution, because if we break a cable, we can more easily replace that with a new one.
So
Okay.
quick question on that. I mean, if you're especially in single mode, you're going to have the insertion, be able to tolerate the insertion loss?
Exactly. That's right. That's right. So all these excellent questions, and there's probably going to be a big trade-off to make there. So that's why this kind of interconnect and the connector it's still being developed. That's part of the ecosystem that's still lagging, in my opinion. Okay, and thermal management. Yeah. So so if we do get a 100 terabit switch, that's going to produce a lot of heat. And so even with very energy efficient optical I/O, let's say if you have 3 picojoule per bit, and you have 100 terabit, so that gives you 300 watts there, but of course your I/O is not consuming all the energy. So if that's only like 15% of the total energy consumed by the IC, that gives you a 2 kilowatt and total power generation by the whole package. So the cooling, of course, without yeah, it's a big challenge. Plus, now you have all these photonics hardware on the perimeter of the package. It's not going to interfere with your heat sink design or heat removal. That's also some open question at this point. So yeah, this is probably my last slide before summary. So light source. Of course, this is every time we meet with DARPA, they ask about how we are doing with the light source. Yeah, so it's apparently a big deal. Without the light source, and the whole thing won't work, obviously. So I mentioned there is some interesting development in some cone laser sources. I'll just quickly summarize here. So one type of cone source is built based on quantum dot GaN medium. So it's a passively mode-locked type of quantum dot laser. It's basically a fiber pearl laser made with a absorber. So in quantum dot GaN medium that can produce multiple laser lines with a big portion of it with relatively equal output power. So the reason why quantum dot is considered as a better GaN medium over the more traditional quantum well is that quantum dot lasers holds the promise to deliver better noise performance in quantum well laser. The mode partition noise is basically just going to kill the signal to noise of each individual line. Even with quantum dot, right now, I think the major technical challenge for this type of light source is the laser noise, the ring noise of the individual laser lines. And also the gain medium for the that may not be wide enough to provide enough of a wavelength range that we would like to fully utilize the spectrum extension spectral range for WDM. But this is very interesting because it potentially can give us a single die, single chip solution with very good wall plug energy efficiency. And another type of cone source is based on nonlinear effect in a micro resonator. It's called Kerr cone. So basically you pump some, I put a little structure picture here. It's made of a few micro ring resonators that's actually built on the wafer. I think these from Columbia, they actually ran the simulation for us when we were talking to them about this. So these are, I think, silicon nitride based micro resonators. So basically you pump light into these resonators, then due to nonlinearity at their high intensity, the one single line turns into an array of lines like a cone. You can control the conditions to, you can design these resonators with different size to control the line spacing, and you can control the conditions to get sort of a wide range of lines above certain power level. And the challenge here is the line power uniformity. You can see right in the middle of the range, you have a couple of lines with low power. And so this is actually a simulated result. Right? So, and according to the simulated result, this device, of course, you pump it with a CW laser, and it's being converted into a cone. So there's a conversion efficiency. So the reported highest conversion efficiency is about 40%. And according to the simulated result, you can go above 60%. But nevertheless, you lose 50% of the power because of this conversion efficiency. So the wall plug efficiency in the end may have a fundamental limit. So that is pretty much it. So this is a summary of the talk. So co-packaged optics promises higher energy efficiency, much higher energy efficiency, much higher bandwidth density, and the potential to reduce latency because you don't need the FEC anymore. So the technology is based on silicon photonics. The basic functionalities today are more or less in place. The ecosystem is being built up. There's still some weaknesses, but it's coming along. And the major challenges, of course, is robust WDM light source with high efficiency and wafer level testing for known good dyes, and fiber attachment, alignment, and fiber management. Thank you.
Thank you, Chuan. Let's take 5 minutes. There's a whole bunch of good questions, but let me see if I think the first one is, how far is co-packaged optics in terms of production and implementation in a data center? I mean, where are we? How far out are we if there aren't existing solutions?
Yeah, that's a good question. I'll try to answer that, but my answer may fall short. You have to consult other experts in this area as well. I know that there are a number of startup companies working in this space. I'll mention Renovus in Canada and also Air Labs here in the US. So what they are trying to do is they are trying to offer the optical engine for co-packaged optics. So basically, they build the optical transceivers with the fiber attachment and everything, and then for the question is still open. Who is going to do the final system integration? Presumably you get this switch IC, you get their optical transceiver modules, then you put them in a common package. They do demonstration, of course, with some IC chip. Then they put their modules in place. I think these companies are getting close to introduce some products. Renovus actually, their product I think is called Odin. I think they are. I haven't checked their website recently, but they have some announcement that their product is getting introduced. It probably is not going to meet the data pipes type of target yet, but that's more likely to be the starting point of co-packaged optics. And Air Labs actually is doing a 8 lambda transceiver, and they work closely with Intel, and they even have a AIB interface between the optical transceiver and the host IC. I think they are also getting close to having a product, but their goal, I don't think their per channel data rate is going to be 50 or 100 gigabit in the beginning. I think they are both Renovus and Air Labs are probably targeting the more modest 25 gigabit per second. So that's what I know. And of course, Luxtera has a good reputation of building optical transceivers based on silicon photonics, and they recently got acquired by Cisco. And I think 2-3 years ago, they were one of the first companies putting forth this co-packaged optics concept. But their technology is based on Mach-Zehnder modulators, and they seem to have some reluctance to go with WDM. Maybe they go with CWDM now because it's Mach-Zehnder based. They can actually do CWDM, and if it's Mach-Zehnder based, I don't think the energy efficiency will be that impressive, and the bandwidth density probably is not the best it can be. But that may be how co-packaged optics get started. Eventually, we probably can get tenfold of improvement in energy efficiency and more than tenfold improvement in bandwidth density, but we probably do not have to reach that threshold to actually commercialize the technology.
So let me ask one last combined question. I mean, if you look at, there are onboard optic modules today to replace the front plate, you know, like COBO Consortium.
Mm-hmm.
And
Mm-hmm.
what challenges are specific for the co-packaged optics that don't exist, that, you know, the same, you know, like the fiber handling, the onboard optical transceivers have those problems today. So, I mean, if you just look specifically at co-packaged optical, what are the specific challenges beyond the onboard optical? And maybe related by that is, you know, your co-packaged optical part is probably not a field replaceable unit like a pluggable transceiver. Right. So how do you deal with failures or quality issues?
That's actually a good question. A quick answer is it's always the downside of higher integration, right? So the higher the integration, the more risk you take in. And, you know, if the part fail, that the cost will be tremendous. But I'm thinking that from a systems standpoint, there could be some redundancy built in at the system level. You can have some spare channels allocated in case there is some partial failure that you can work around it. Just like you know, today people do in memory and in other electronic circuits, right? And from a challenge standpoint, I think it's just more and more. I mean, so the fiber density will be even higher if you put all the fibers attached to the package, or at least put the connectors directly at the package. I think whatever the challenge you already have with COBO, with onboard optics, I think it's just going to be even more. I mean, so COBO is kind of an in-between type of approach. It does not quite eliminate the need for a high-speed, relatively high power consumption electrical interface between the IC and the optical module. It probably increases the density to some degree, but yeah, not as much as a co-packaged optics can actually deliver. Yeah, that's pretty much the answer I can provide at this point.
Thank you, Chuan. A great presentation. There are a large number of questions that we're just not going to get to. I'll send them to you, and hopefully the people with the questions will reach out to you directly. But I thank you very much for a great presentation and really giving a great overview of the challenges. So thank you.
Yeah, thank you. Actually, I apologize for running much longer, and thank you very much for having me here.
So just a reminder, next presentation will be on November 11th, followed by the 25th, December 9th, and December 16th. We'll do our holiday hangout. So thank you again, and I wish everybody a good rest of their day. Thank you.